Let's discuss the photoelectric effect. Let's say there is a vacuum tube with two electrodes, E emitter and C is the collector, connected to voltmeter, emitter and a variable potential difference. When light falls on the emitter, electrons are ejected from emitter and they go towards collector, and thus you have photo current flowing in the circuit. So again, when a beam of light of high frequency, or that is low wavelength, falls on a metal plate, here which is emitter, electrons are removed from metal surface. These electrons, which are known as photoelectrons, with kinetic energy move towards collector and produce current in the circuit, and this current is called photocurrent. This entire process is taking inside a vacuum tube, so electrons do not lose energy in collision with air molecules. In 1905, Planck's ideas were taken and extended by Einstein, who showed that they explain several phenomena, the most important of which was the photoelectric effect. At first sight, this process, which is the basis of some modern light detecting devices, appeared perfectly consistent with the classical EM theory. Light waves were known to carry energy in the form of oscillating electric and magnetic fields, and it seems perfectly reasonable that some electrons in the metal could absorb enough of this energy to be ejected. However, closer investigation showed that several features of the process were incompatible with the classical electromagnetic theory. Now let's look at a couple of experimental observations. If collector is kept at higher potential, it attracts electrons, causing current in the circuit. And here the magnitude of current indicates the number of electrons ejected. However, now if a collector is kept at a lower potential, it repels electrons, and only those electrons with enough kinetic energy to overcome the retarding potential V0 reaches the second electrode. Now, if we keep on increasing the retarding potential, the current will eventually drop until at a certain stopping potential Vs, all current ceases, and thus at that point kinetic energy will be maximum. So as the potential difference in the circuit reaches this stopping potential Vs, then even the most energetic photoelectrons do not have enough kinetic energy to reach plate C or collector. So at that point this Kmax is equal to EVS. Graphically, if I now plot current or photocurrent in the circuit as a function of retarding potential, it will look like this. Now let's look at some experimental observations. Let's first look at effect of intensity of the incident light. If this is the plot for current versus retarding potential for one intensity of light, if we double now the intensity of the incident light, the current in the circuit increases, but the stopping potential remains same. Therefore, for fixed wavelength of frequency, maximum kinetic energy or which is equal to EVS, Vs is the stopping potential, is independent of intensity of the incident EM wave. Now let's look at effect of frequency of incident light. If we plot now the variation of current with retarding potential, so for a incident light of a certain frequency f, this is how the graph looks like. And for a wave or incident light of higher frequency, stopping potential, we will see that it's much higher. Now if we keep varying the frequency and keep measuring its stopping potential, we can get a plot for stopping potential versus frequency, and we will see that it varies linearly. If we extend that graph, we will see that it reaches zero stopping potential at a certain frequency f0 that we call as threshold frequency. So from this graph it is clear that photoelectrons cannot be emitted if the frequency of the incident light is below a certain value or below threshold frequency. Here, note that this threshold frequency is different for different materials. And the third experimental observation was that the first photoelectrons are emitted virtually instantaneously after the light source is turned on. The light source, as soon as it is incident on the metal, you see photoelectrons or you see photocurrent flowing in the circuit. For example, according to the classical theory, the first electron should be emitted in time interval of the order of seconds after the radiation begins to strike the metal surface. Anyway, you can read in more detail why these observations could not be explained by classical theory. Here now I will discuss the quantum theory of the photoelectric effect. Now, based on Planck's idea, Einstein proposed that the energy in a beam of light, here incident light, is not distributed continuously through space, but it consists of finite number of energy quanta which are localized at points which cannot be subdivided and which are absorbed and emitted only as a whole unit. These are bundles of energy or quanta. The energy of single quantum is equal to hf. Here h is Planck's constant and f is the frequency of the incident wave. Now, since it seems unlikely that two photons would strike one electron, Einstein argued that each ejected electron must be the result of a single photon giving up its energy hf to the electron. With these assumptions, both of the properties mentioned previously are easily explained. Now, two properties of these photons are first, it's a massless. Second, photons carry linear momentum and energy. And these photons travel at the speed of light. Therefore, they must obey relativistic relationship. Momentum equals to total energy divided by speed of light. So we get P equals to h over lambda. Photons carry linear momentum as well as energy, and therefore they share this characteristic properties of particles. Now before we go further, let's define the term work function. So for any given metal, we know that there is a definite minimum energy needed to remove an electron from the metal. This minimum energy is called the work function. And we have seen that when a light falls on a metal surface, the entire energy of photon, which is E equals to hf, is delivered instantaneously to a single electron. Now if this photon energy is greater than the work function of the metal, photoelectric effect will occur and photoelectrons will be released. But since hf is greater than the work function, the excess energy appears as kinetic energy to the photoelectrons because they need energy to move to collector. So when energy hf is of a photon is given, it is partially used to remove electron from the metal surface, and then rest of the energy goes as a maximum kinetic energy to the photoelectrons. We can rewrite this equation to get kinetic energy of photoelectrons. And this kinetic energy or maximum kinetic energy is also equal to EVS, where Vs is the stopping potential. We have seen this earlier. So note that intensity of the light source does not appear in this equation. Now if the energy of photon is less than the work function of a metal, then photoelectric effect will not occur because it does not, the electrons would not have enough energy to remove from the metal. So if the photon energy HF is less than phi or less than the work function, we have seen that no photons will be able to eject any electrons. So that means there is a smallest or there is a minimum frequency needed for the incident wavelength, so that this work function is equal to HF naught or the threshold frequency. So now the above equation can also be rewritten as here. If you want to use any of these equations, just make sure the unit for energy is same in both sides, left side and right side of the equal sign. Now if you remember our first experimental observation, when the intensity of the incident wave was increased, we still got the same stopping potential. And we know that stopping potential is directly related to the kinetic energy of these electrons. Now, how can we explain the first point by quantum theory? So, or Einstein's theory. So, if intensity of the light is increased, the number of photons is increased, but the energy HF of an individual photon remains unchanged. So now if more and more photons are coming onto the metal, more electrons will be ejected. But each of the photons has the same energy, so each ejected electron will also be given the same energy. Therefore, maximum kinetic energy will not change, and hence the stopping potential will remain same. So this description can give the explanation for this graph which was observed experimentally. Now, if we look at the most important equation from Einstein theory to explain this photoelectric effect, this experimental test of this prediction proved difficult, but it was successfully carried out by Robert Millikan, one of whose trials in 1916 is shown in a graph below. Millikan observed the photoelectric effect in sodium, and this is how he got the plot, and he was able to determine the threshold frequency also in case of sodium. Now let's look at one example. The work function of silver is given as 4.7 electron volt. What is the potential Vs needed to stop all electrons when ultraviolet light of wavelength 200 nanometer shines on the silver? Here we can first calculate the energy of UV photon using the formula E equals to hc over lambda, and you can substitute the value of h, Planck's constant, in electron volts, or you can we get maximum kinetic energy of 1.5 electron volt, and from here we can calculate the stopping potential to be equal to 1.5 volt. Now just to tell you how you can get the value of Hc in terms of electron volt meter, let's see what we can do.